joining this webinar. I'm Michele Merelli, part of EngineSoft and ParticleWorks team. And today we will discuss how recent advances in graphic cards computing units can speed up simulation. So we will take a look at how different GPUs can speed up simulation of ParticleWorks. Okay, so I will give you numbers. I will give you a little bit of an overview also of trends and costs on the hardware side. So it's very interesting because as you might have seen, NVIDIA is increasingly pushing, thanks to AI, to better architectures. And it's interesting to see that also simulation and moving particle simulation more specifically can take advantage of that. So this is the agenda of today. We have a first introduction, general introduction on GPU computing and how it's scaling up. It's been scaling up in the last 5 years, I would say. Then slightly on ParticleWorks that you might be familiar with already, so we'll not cover in detail the method or the application, but just a quick overview. And then we will go through the hardware selection question, like how are GPUs compared to conventional CPU cores? And then what GPU should you buy for ParticleWorks? And at the end, we will focus also on the software side, because it's interesting to see that, of course, when we have to decide the hardware, when we buy a predefined package, it's very easy. We say, okay, yeah, we spend more, we double the amount of computing power, and that we expect to scale linearly. But of course, under the hood, we have a lot of more engineering and optimization going on. So we will see how also the software can be speed up with the right, let's say, algorithm and implementation. The first question I'm asking to you, are you following the trend? The trend is clear. This is a graph showing the GPT-3 inference performance. So it's an AI application. But we can clearly see that in the last 3.5 years, those performances were increasingly quite significantly. In the latest NVIDIA keynote, they presented the BlackRock architecture, and it's stunning. The amount of compute they are able at NVIDIA to put on a chip nowadays, it's really remarkable. So we see like a speed up of 20-fold in just 3 years, even more actually. And at the same time, so here is a quick overview of the compute revolution that, let's say, specialized computing architectures are allowing nowadays. So this is Moore's law and single-threaded CPUs architectures. And when we come to heterogeneous specialized architecture, and GPU is one of them, so graphic cards are one of them, we see that the growth has been faster actually than Moore's law. So 2 times per year. So that resulted in a 1,000 growth in the last 10 years, and we increasingly see the same trend. Also with the latest release of the RTX 4090, the gaming GPU from NVIDIA that also ParticleWorks support. So the question is, of course, are you following the trend? Because increasingly simulation is more affordable. If we look at the cost per flop per second, so actually these are the flops per second. So the, let's say, hardware iteration per second that you get per amount of dollar, you see that we are basically in the last 10 years, we went from 4 billion to 40 billion. So 10x on the dollar you spend on compute, okay? And at the same time, there is another trend that is in the opposite direction. We all saw what, let's say, cost inflation brought to us after the supply chain shocks that followed geopolitical or let's say pandemic issues. So to test and to develop in the traditional way e-motors, engines, pistons, or any other engineering, let's say, product is increasingly costly, okay? Because materials availability to create like a prototype, for instance, are more and more higher, the price and at the same time also the preparation of this model time. And we see, of course, the trend of increasingly digital R&D process and early simulation. Simulation is increasingly earlier in the R&D workflow. Why? Why? Especially because we have new simulation tools like particle simulation that allow for fast model and simulation workflow. The reason is shown here. So if we compare conventional CFD method with ParticleWorks MPS method, we don't have to generate a computational mesh at the beginning of our simulation workflow. So in conventional CFD, finite volume CFD, you have to clean the geometry, to remove some features that might, let's say, create small gaps and then might result in failure of your simulation. With moving particle simulation, we actually make the generation of the computational node automatic. So the software automatically creates particles that are the computational nodes on which the same equations are solved. And at the same time, we have faster and more stable simulation results, okay? But it's also very interesting to see that the algorithm behind, so MPS, is actually intrinsically parallelizable, okay? As compared to finite volume method, MPS algorithms can be parallelized very efficiently, and because of that, we can use GPU compute together with CPU compute. So GPU, graphic card computing, was always possible in ParticleWorks. Later on, from 2022, actually multi-GPU, so the idea to combine more than one GPU was also introduced, and we will see the scaling factor achievable with that. So just to give you a quick overview, ParticleWorks handles fluids, but also other aspects of the simulation workflow, like conjugated transfer simulation. So we can also look at temperature in fluid and solids. So effectively, we have a solver that can run multi-phase with air or with powders material fluid simulation, okay? So to have more details on the application, I will reference to you later on our website where you can find more information if you like, or our, let's say, email. So because the mesh generation step is not required, as mentioned, the simulation workflow is much faster. We directly work with the CAD. The CFD setup is set up directly in the workflow. And here you see the GPU acceleration effect. So simulation time can be reduced given a certain hardware or given a certain amount of money to allocate for computing quite significantly because of the speed up we mentioned at the beginning. So just to give you some numbers, here is the full workflow that now allows for 1 day from CAD to simulation results workflow. Mesh-based CFD for the topics that we usually cover with Particle Works takes more than 1 week, actually, especially because the pre-process and post-processing times are much longer. So just to summarize, with this method, we don't need the mesh generation. So actually, the CAD design by design engineers can be directly used for the simulation. We don't have to prepare the fluid volume and so on. We have a very simple workflow and simple numerical setup. So you don't have to be a CFD wizard. You don't have to be expert on computational hydrogen engineering and computational fluid dynamics to run a simulation with Particle Works. And because we can use GPUs, we effectively can move from clusters to just a compact workstation. We will see an example in a second. Here, just to remind you, are some of the applications like engine or piston cooling, bearings, lubrication, e-motor cooling, sloshing in transmission. So also if you have lubrication of big transmission with complex geometries and complex rotating elements, that's no issue. Soiling, wading type of simulation. A lot of phenomena related to automotive, but actually we have example also in the mixing, in the pharma, concrete modeling. We have several other food and beverage application, several other fields. So again, if you're curious to see where this software is applied, please check our website and I will provide some reference at the end. Okay, so now the big question, how are GPUs compared to CPUs, and what GPU should you buy for Particle Works? So as a disclaimer, before we dig into the numbers and the, let's say, simulation times I will provide are just based on standard benchmarks we will see. So very basic, let's say, Particle Works project with basic physics. Of course, when we start to enable other aspects of the solver, we might have different scaling or different simulation time. Ultimately, what we suggest to our customer is to run their proprietary model on available hardware, and we can also run on our hardware to suggest possible improvement on the hardware side, given our know-how on how a certain model should scale. And also I will present a list of CPUs and GPUs, but there are more than, there is a wider selection of those other than the one presented, okay? So please don't think that what we show is the only hardware compatible with Particle Works, and just ask us, we can give you more information. So let's start from here. Here we see how a CPU, actually 50 approximately CPU cores, can be compared to GPUs. So those are NVIDIA GPUs. Actually, V100 and A100 are two of the best-in-class GPUs. And then we see the multi-GPU scaling. But as a starting point, we see that 48 GPUs are actually 7 times slower than one V100. So approximately here we see that one V100 can be already compared to 250 or 300 CPU cores. And then the scaling goes on, because if we improve the GPU, we actually have a 10x speed up as compared to reference for A100, up to approximately 40x. So what we see is that for A100 can perform like a cluster of 2,000 CPU cores for specific projects, especially very big projects in terms of numerical, in terms of number of particles or computational nodes. So we can run on both CPU and GPUs, but it's clear that GPUs are much faster. If you want to compare different GPUs, my suggestion is to go to Technical City, this website. It's very easy to see and compare maybe your available hardware with other hardware, the hardware presented, so you can follow this link. And on that website, you will see that you have some numbers, and the most important one for us, just to have a rough estimation of simulation time or scaling time, is to look at the CUDA cores and boost clock speed or core clock speed of the hardware. Because if you take a look at how the CUDA cores, so the, let's say, CPU embedded cores on the graphic card, or their clock time, if you look at those ratios or those increasing factor, you can have an idea of the speed up you will obtain. For instance, in this comparison, A40 with 4090, we see that we might expect a speed up of 2, given these numbers. Of course, you have also power consumption, and you want to address that because you have ultimately to also cool that power consumption. So depending on some hardware or some workstation setup, you might be able to accommodate or not certain GPUs. So on the multi-resolution, on the multi-GPU, so scaling, we already saw that we can scale simulation time using more than one GPU. But just to give you a little bit of a closer look on that, we ran this quick benchmark case, a gearbox case, with 2 configuration of particle size, so 2 resulting number of particles, because if we change the particle size, the number of particles given a certain amount of volume will of course change. The lower the particle size, the higher the number of particles we need to discretize this volume. And we ran scalability on A40 with different number of GPUs, up to 8. Of course, we will see that given the complexity or the number of computational nodes, we see slightly different scalability. And that makes sense because it's pointless to run on thousands of cores if the model is small. So here we see exactly that. We see on the left 10 million particles and on the right 30 million particles. We see that for 10 million particles, the reduction of simulation time when we increase the number of GPU is smaller than on the 30 million particle. So effectively, we have a factor of 2 simulation reduction time when we go to 4 GPUs in the 30 million situation. That factor of 2 is achieved only with 8 GPU at 10 million particle. Again, because here the system is not, let's say, overloaded, okay? So it doesn't make sense to parallelize too much here because we don't have a lot of computational nodes. But the message is that we scale differently depending on, again, the given simulation and the given number of particles. Here we see a comparison of different GPUs. It's very interesting to see that RTX 4090, a gaming GPU, can actually outperform more scientific but older GPUs. So this one, the V100, was released 3 years ago, and we can see that basically for 1/3 or 1/4 of the price, we have better simulation time. But yeah, you get an idea. We can already have a speed up of factor of 2, just changing the GPU and updating to a new one. And then we see here other scaling for RTX 2080 for a model of 5 million particles. Okay, so again, in general, we have approximately for small models a factor of 2 every 4 GPUs. But we have better scaling if we increase significantly the number of particles. We will see in a second. So this is another slide basically discussing the same scaling, actually the same numbers I showed you before. So on a traditional standard model, we see that 4A100 can be 40 times faster than, let's say, 48 CPU cores. I want to come back to the model size. So as I mentioned, the scalability with multi-GPU is far better. You see here that basically by going from 1 to 2, we have acceleration rate of 2. And then when we go to 4, we have acceleration of 4 if the model is very big. So in this case, you can also have a look at the dimension of the project we can handle, both on the number of particles and of course also the GPU memory needed to load all the models and all the particles, okay? So effectively, we can easily handle 200 million particle projects and 300 gigabytes of GPU memory usage. Because we will see also in a few slides that GPU memory is also, of course, important for some application. So this is an extreme example, but it's just to give you an overview of how well we can scale and how big of a project we can run. And here we see that it's not only the moving particle simulation solver that benefits from multi-GPU or the scaling. Actually, here is a simulation where we couple the moving particle simulation fluid with the conjugated transfer solid simulation. So you see here the temperature in the solid for DC motor. This is something that we can do and we can have a look at. So not only solving for the fluid phase, but also, as mentioned, the solid phase. And interestingly, we see that we have very good efficiency of scaling also for this double precision conjugated transfer solver. So again, it's not a guarantee that we get this kind of scaling because there are underlying different algorithms, different coupling between the two solvers. So it's very impressive stuff, in my opinion. And here we see just a quick overview of some numbers when we want to compare the officially supported GPU for particle works. So we report a number of CUDA cores, again, taken from the website I showed you before, the cost in thousands of euro, the clock speed, and the GPU RAM. So you can have an idea of course, the best-in-class latest release 4090, that is very impressive in terms of CUDA core and clock speed, and also price. But yeah, you can see that we have two kinds of GPUs. One is the gaming GPU sector that is very cheap, usually with smaller GPU RAM, and it's a type of hardware that handles single precision usually very well, but struggles with double precision, and in some cases we might need double precision compute. Actually, just 5 or 10% of simulation require double precision compute, but there might be some cases. And down here we have like the scientific Quadro, or like yeah, more enterprise type of GPU and hardware solution. So for more stable and reliable hardware, of course, those are very well supported, and they are the most ideal in terms of let's say, guaranteeing the performance over the long term. And again, we have the benefit of higher GPU RAM. So in some cases, we can handle bigger models with this kind of GPUs. So we are also announcing today our partnership with Sistemi HS. It's our technology solution provider, and together with them, we can build custom-made hardware and sell it to you together with the software. So effectively, we can build a tailor-made, easy-to-use workstation given your requirements and your budget, of course. So just feel free to reach out if you're interested to know more on that. It's not only hardware, it's interesting to see that also software updates and new feature can speed up the simulation workflow. Here we see that with the newest version of ParticleWorks, actually just by improving the underlying algorithm and the allocation of the memory, we see a 20% reduction of simulation time. So it's very interesting also because in a few months we will have a new release of the software, and of course this speed up is expected to continue. Moreover, in the latest release we got the multi-resolution feature. So the idea that we can discretize with a smaller particle size inside a portion of the domain. We can discretize the fluid with that smaller particle size. So we are not, so let's say we have a small gap and we need to have a small particle size to resolve for that small gap or small channel. Yeah, previously you had to discretize everywhere the domain with that small gap. So of course, resulting in many particles, and that resulted in longer simulation time. Now we can be smarter, and we can define boxes or regions where the particle is redefined, as shown here. So decreased in particle, and then it's converted back to the bigger particle where not needed. We have a clear example here of simulation time decrease thanks to that feature. So we have a soiling type of application. You see here we have small gaps in the cooler of the, so the water can go through some geometry elements of the car in the front there. And because of the gap dimensionality here, we might need a particle size of 5 millimeter, but if we discretize at 5 millimeter everywhere in the domain, we have actually a lot of particles. So the idea could be to use a multi-resolution region in red here, slightly visible, such that the particle size is smaller only in that region, and elsewhere is 10 millimeter as in the initial simulation. So we can see here that by using multi-resolution, we can move from 8 hours to 3 hours, okay? As compared to just keeping particle size 5 millimeter everywhere in the domain, okay? So of course, also here, we might have different scaling or different setup depending on the number of particles you have for each case, but in general, it's a very good and promising simulation reduction time. So here we have another example on just around the track. We have a box following the track that basically creates smaller particles, so a multi-resolution region. And we can see in light blue the particles then impinging on the car and yeah, wetting some areas of the car. And here, lastly, another example, it's an e-motor with a very small gap in one distributing channel of the cooling circuit. So the gap is just 250 micron. So without a small enough particle size, we could not see flow through that. And we have an example here. So at 0.3 millimeter, you can clearly see that the gap it's not resolved. But by using a multi-resolution combination of approach, so basically here we have a refinement region, we can afford the 0.3 elsewhere in the domain and then 0.1 just where the gap, the small gap is. So that results in a simulation time that can be 50% faster, okay? So reduction of factor of 2. So as you can see, we have both hardware and software pushing for faster and cheaper simulation solution. And again, in the next actually ParticleWorks experience, this one is from last year. It's a conference we organize annually, and that this year will take place in September in Frankfurt, Germany. So at the next ParticleWorks experience, the developer of the software will discuss in detail the new features and also the new speed up capabilities of ParticleWorks. So if you're interested, you can register, it's free, and you can join us in Frankfurt next September. Having said that, I think I covered most of what I wanted to cover today, and I'm very happy to address your question and your remarks if you have some. So please, you can write in the chat those questions. I see John asking if the scaling is independent of the problem type. As we saw, it's not independent. It depends on the number of particles. It depends on the numerics, so like pressure solver, temperature solver, and so on. And also it depends on what feature of the software we enable, like if we start to solve for conjugated transfer, we have slightly less better scaling, and so on. We saw it, I think, in this slide here. So as compared to, let's say, regular CFD simulation with, let's say, effectively full scaling, when we look at CHD type of simulation, we have 60% efficiency in the scaling. I hope that that answered your question.